Navigation problems. We're in a boat. It travels at a velocity of 4.5 meters per second south across a river. The river current is 2.0 meters per second east. What is the velocity of the boat relative to the shore? Okay, for this I like to draw it all out. So here's the shore, both sides. Here's our directions. So the water itself, the current is 2 meters per second east. So it's traveling this way. Okay, now we're in a boat. Here it is, a little dinghy. And it can travel 4.5 meters per second south. So that boat is going to start right here on the shore. And it can travel 4.5 meters per second south. So if there was no water here, if there was no current to the water here, and we were just sitting in a still pond that wasn't moving, this boat would travel 4.5 meters per second and get to the other side right here, just directly across from where it started. However, we know that there is a river current, and that river current pushes it along this way, because it's moving 2.0 meters per second east. So this boat, even though it's headed directly straight, it's pointed straight, it ends up heading this way because the current pushes it downstream, and then it ends up over here. So we can draw, it starts here, it ends here, we can draw in our resultant velocity vector. Okay? This is our resultant. And this right here is the angle that the boat travels relative to the shore. So this is a right angle triangle. We can solve this with our standard Pythagorean theorem. First of all, let's get r. And we know the equation is r squared equals 4.5 meters per second squared plus 2.0 meters per second squared. So if we square root each side, we get r equals the square root of 4.5 meters per second squared plus 2.0 meters per second squared. Okay, so we can use our calculator to get the answer to that. You can even just punch it all in as 1. 4.5 squared plus 2 squared, square root of that, gives us 4.924. So, our speed is we'll just use 92 meters per second. Okay? And so the boat, even though it can travel at 4.5 meters per second in still water, it's being pushed downstream by this moving water, and so this resultant vector right here is actually moving at a higher speed relative to the shore. Now we want to figure out this angle. Remember, tan theta equals opposite over adjacent. Okay? And we want to solve for theta. Opposite is 2.0. Adjacent is 4.5. So we can rewrite that as theta equals tan inverse of 2.0 over 4.5. And again, we'll use our calculator to solve that. So let's find tan inverse. 2 divided by 4.5. And we get 23.96 degrees. So theta equals 23.96 degrees. So because there's a current, the boat gets pushed downstream, and that makes its movement relative to the shore at a bit of an angle. That angle happens to be 23.96 degrees. So when you write in your final speed, you write in v equals, and it was 4.92 meters per second. We have 2 significant digits for each at the beginning, so we're going to use 2 here. So that's 4.9 meters per second. However, we want the velocity. Okay, so that's a vector. And we need a direction, which we have right here, and that's 24 degrees. Again, two significant figures. And if you want, add in where it's actually moving. So you can put it from here or from here. I'm going to go this way. So what is this direction? We're looking at east of south. East of south. And that's a pretty typical navigation problem that you're going to find. Okay? Let's do a second. If a swimmer can swim with a speed of 2.5 meters per second, find the angle that she must direct herself in order to cross a river directly that is flowing with a velocity of 1.5 meters per second east. Okay. So keeping it simple by having the shore and water moving in the same direction, so you can picture this. Again, this is north. So, but the question is worded differently, right? We want to find out what angle she must direct herself in order to cross a river directly. So that means if we have our little swimmer here, she wants to go in, it's female, so, and land directly across the shore. Okay? Start here and get there. But we know that if she just jumped in and pointed herself straight across, that the current would eventually push her this way, and if she tried to, she'd probably end up somewhere over here if she pointed herself straight across. Okay? So she wants to end up here. How is she going to do that? If she goes straight across, she ends up downstream. She wants to end up right here. So what she should do is point herself in this direction. Okay? She wants to go this way. Okay? So that as the current pushes her downstream, she ends up right there, exactly across from where she started. So, she wants to go this way. The actual current pushes her back, and then she will end up moving directly that way. What do we know? We know that the current is flowing at 1.5 meters per second east. Okay, she can swim with a speed of 2.5 meters per second. So this is her swimming right here. So this one right here is her swimming at 2.5 meters per second. All right, swims in this direction, current pushes her back, and then she ends up directly across from where she started after jumping in. We want to find this angle. What angle does she want to point herself to end up right there? So we're going to use SOHCAHTOA, and let's use values that we already have. 2.5 is the hypotenuse, and 1.5 is opposite of theta, so we have opposite and hypotenuse. So let's make it easy on ourselves and use sine. Okay? So, for us, opposite is 1.5, and hypotenuse is 2.5. So we rewrite this for theta. It equals sine inverse of 1.5 over 2.5. And now we use our calculator. Sine inverse of 1.5 divided by 2.5 gives us 36.87 degrees. Equals 36.87 degrees. Two significant figures. We're going to use 2 again. So we're going to say that the angle has to be 37 degrees that she's going to point herself in. However, what is that? She is going this direction from here, okay? So she has to point herself west of south for this to work. 37 degrees west of south. Notice, in this problem, this is her traveling. Her speed is on the hypotenuse. Notice in this problem, this is what the boat can travel in still water, and it's this vector right here. So try to conceptualize how this is going to look. Draw out the problem and figure out which one is going to be the actual speed of either the boat or the swimmer in still water. Okay, so the second type normally involves airplanes, and we can use these subscripts, though you don't have to. So VA is the plane's velocity relative to air. We call that airspeed, and their direction is heading. VW is the wind velocity. We call it wind speed and wind direction. It's pretty obvious. And VG, that's the plane's velocity relative to the ground. We call that ground speed, and the direction is track. Okay, so you might have questions that are worded this way. I find that the speed one kind of gives it away. You're either looking for airspeed, wind speed, or ground speed. A, W, G. Okay, and then you just have to remember the direction ones. So let's do one. An airplane is heading east with an airspeed of 120 kilometers an hour. Let's draw it. This is north, 120 kilometers an hour. A 40 kilometer an hour wind is blowing toward the south. Toward the south looks like this. This is east, this is south. So, draw the vector diagram. Well, this one's pretty straightforward. We start here, we end here, put in your big double arrow, and this is the resultant velocity vector. However, let's label these using the proper notation. This, that we're given, 120 kilometer hours, is the airspeed. Okay, so this is VA. We're also given the wind is blowing toward the south. Okay, so this is the wind velocity. And that leaves us the resultant as the ground speed. Okay, so you can figure this using regular Pythagorean theorem and find out what the ground speed is. You can calculate the angle, and you can use that to figure out, if you look here, direction is the track for ground speed. Okay, a pilot wants to fly west. The plane has an airspeed of 100 kilometers an hour. There's a 10 kilometer an hour wind blowing from the south. We'll get to that. Calculate the pilot's proper heading and ground speed. Okay? Proper heading and ground speed. Let's look at this for a quick review. Heading is the direction for the plane's velocity relative to the air, and ground speed is the speed for the plane relative to the ground. Okay, so first of all, we draw it. This is north. The pilot wants to fly west. Okay, so the pilot wants to start here and end here. He wants to go west. Okay, there's a 10 kilometer an hour wind blowing from the south. The wind is blowing from the south, not to the south. Okay, it's blowing from the south. It's actually blowing this direction. From the south, it's coming from here, it's going that direction, so this is what it looks like, 10 kilometers an hour. And it's going north, because it's from the south. Calculate the pilot's proper heading and ground speed. So, they want to go west, but the wind is blowing up. The wind is going to blow them this direction. Okay? So if the pilot just headed straight directly for his location, the wind would blow him off and he would be way up here. Okay? So to end up directly across from where he wants to end up, right here, and he has to angle himself this way to actually get there. Okay? So let's label these. This is the wind speed, right here. This one is the airspeed. And this one is the ground speed. So let's relabel these with the actual values so that we can use them to answer this problem. VA, we're given 100 kilometers an hour. VW, we're given, it's 10 kilometers per hour. VG, ground speed, we're trying to find that. Okay. And then the heading is what direction they're actually going to go. So, this is the hypotenuse here. This is opposite. This is adjacent. We're trying to figure out this one first. Let's use regular Pythagorean theorem. So c squared equals a squared plus b squared. That means 100 kilometers per hour squared equals 10 kilometers per hour squared plus ground speed squared. I labeled it with a vector. It's not a vector yet. This is speed. Okay, so if we rearrange this, you get ground speed squared equals 100 kilometers per hour squared minus 10 kilometers per hour squared. Okay. If you take the square root of each side, then we will find ground speed. And let's use our calculator to get this answer. So, 100 squared minus 10 squared. And we want the square root of that whole thing. Square root of 100 squared minus 10 squared. 99.499. Kilometers per hour. Okay. Now we want to find out this angle, theta. Okay. Usually we were using tan. However, it's better practice to use the values that you're given. Okay, in this case we have opposite and hypotenuse. And that's going to be sine. Opposite in this case is 10. Hypotenuse in this case is 100. So theta equals sine inverse of 10 over 100. So we'll use our calculator. Sine inverse 10 divided by 100. 5.7 degrees. Okay. Significant figures. We really don't have very many. So when we're going to quote this, let's just use 3 for accuracy for this question. Okay. Velocity for ground So let's state the proper heading. We know that we're going 5.7 degrees. That 5.7 degrees is down from here. Okay, so this is going south of west. 5.7 degrees south of west. So when we state this, we're going to say that that angle is 5.7 degrees south of west. And remember that you could also say that we're going this way, from this direction. Okay, if this is 5.7 degrees, then this one would actually be 84.3 degrees if you wanted, and that would be west of south. So this could also be 84 degrees west of south. Okay.